Brian from Seattle on November 12th, 2025. And today we're going to cover auroras and geomagnetic storms, given the fact that we just had a G4 severe storm last night that caused quite a show. But first we're going to cover today's news. The first is a security story about Bluetooth. Bluetooth 6.2 brings major security improvements and ultra-low latency. And this is from Jean-Luc Offranc, CNX Software. The Bluetooth Special Interest Group just released Bluetooth 6.2 and is packing some serious security improvements alongside performance upgrades that could transform how we think about wireless connectivity. The headline feature is protection against sophisticated amplitude-based RF attacks that target proximity and distance measurements. And this is a critical defense for the growing ecosystem of devices that rely on how close am I as a security factor. So here's what's actually happening under the hood. Attackers can manipulate radio signal amplitude in sync with Bluetooth symbol timing to create predictable phase distortions that fool devices about distance. By amplifying signals at precisely the right moments, they can make a car think that your key fob is right next to it when you're actually across the parking lot. Bluetooth 6.2 fights back with a Normalized Attack Detector Metric, an NADM. That uses discrete Fourier transform analysis to spot these crafted attacks by looking for telltale energy peaks at specific frequencies. So this matters more than you might think. Beyond obvious targets like keyless car entry and smart locks, this specifically hardens channel sounding distance measurements. While this could theoretically affect any system that truly depends on precise ranging, many passkey flows use BLE for proximity presence rather than distance measurement. So this impact is more limited. The security of typical passkey sign-ins doesn't rely on Bluetooth's security properties or precise ranging values. And that's critical. A lot of you have started to have sites ask you to use passkeys, where you might take a picture of a QR code from your phone, or you establish a passkey that you can use that's dependent on your device. What this is saying is that this particular range attack doesn't really rely on the same mechanism. Here's where it gets interesting for gamers and VR enthusiasts. This Bluetooth 6.2 slashes the connection interval from 7.5 milliseconds down to just 375 microseconds. That's a 20x improvement in responsiveness that could eliminate the lag that makes wireless VR headsets and gaming controllers feel sluggish. The specification also introduces bulk serialization mode for USB Bluetooth devices, and that should make LE audio integration smoother. With Bluetooth moving to twice-yearly releases, we're seeing rapid evolution in what was once a very slow-moving standard. And let me pause here to put a quick definition in place. What is Bluetooth LE? You've probably heard people say Bluetooth LE. No one explains it. I will. Bluetooth LE is Bluetooth Low Energy. It's the wireless technology designed for short-range communication that consumes far less power than Bluetooth Classic. So it's ideal for devices that need to transmit small amounts of data, such as fitness trackers, smart home sensors, wireless keyboards. It can operate for long periods on small batteries. So while it has a lower data rate than Bluetooth Classic, it's much more energy efficient. And we have a pair of programming stories today. One is YouTube forces YT-DLP to require external JavaScript runtime. Some of you might have the first question, which is, what is YT-DLP? And let me put it in perspective. If you do something like make a YouTube video, or someone sends you a YouTube video, and you want to extract it and save it locally, or you want to save the audio somewhere, like what I had to do for one of my previous podcast episodes, you use a tool like YT-DLP, or you use a tool like FFmpeg. So YT-DLP is essentially the open source video downloader that you can use to download a video or audio from YouTube. And Google's latest changes to YouTube have forced this popular open source video downloader, YT-DLP, to require an external JavaScript runtime like Node.js or Dino for full functionality. This represents a significant architectural shift for a tool that previously worked as a standalone Python application. The YT-DLP maintainers announced that version 2025.11.12 now requires users to install additional software just to download videos from YouTube. This is highlighting an ongoing cat and mouse game between Google and independent developers who build tools around YouTube's platform. By making their video extraction process more dependent on JavaScript execution, Google has essentially forced YT-DLP to become more complex and harder to deploy. The move affects millions of users who rely on YT-DLP for archiving content, accessibility purposes, or simply downloading videos for offline viewing. It's a classic example of how platform changes by big tech companies can ripple through the open source ecosystem. And this forces developers to constantly adapt their tools just to maintain basic functionality. And our second programming story of the day is related. FFmpeg developers tell Google, quote, "Fund us or stop sending bugs." This is from Stephen J. Von Nichols of the New Stack, and this was a story that was referred to me by a dedicated listener named Colin Henry. Thank you, Colin. So speaking of the conflicts between Google and open source projects, the FFmpeg developers are having their own heated Twitter exchange with the same tech giant. The Von Nichols story at the New Stack also explores the frustration. The FFmpeg team says, is it fair for trillion-dollar corporations to use AI to flood volunteer-maintained projects with security reports and then expect free fixes? FFmpeg pointed out that they're written almost exclusively by volunteers while being critical infrastructure for companies worth billions, even trillions. Google does offer a patch rewards program, but FFmpeg says it's too limited with 3 patches per month cap. This isn't just about FFmpeg. The libxml2 maintainer also recently quit for similar reasons, saying he was spending several hours each week dealing with security issues reported by third parties with no compensation. It's a perfect example of the open source sustainability crisis where critical internet infrastructure depends on unpaid volunteers. Our weird bucket story for the day is stickertop.art. It's celebrating the lost art of laptop personalization. And this is from Jack Ganji at stickertop.art. Someone has created an entire website dedicated to documenting the dying art of laptop sticker culture, and it's surprisingly captivating. Stickertop.art is a curated gallery of laptops from around the world, each covered in stickers that tell the story of their owner's interests, travels, and digital identity. From cyberdeck-style modifications with samurai themes to corporate ThinkPads covered in open-source project logos, each submission captures a unique slice of tech culture. What makes this fascinating is how it documents something that's quietly disappearing. As laptops become thinner and more premium, fewer people are willing to plaster them with stickers. The site becomes an archive of a particular moment in tech culture when your laptop was a canvas for self-expression, not just a tool. You can see everything from conference stickers and band logos to programming language badges and obscure internet memes. I'm personally surprised by the story because I actually just started to put stickers on my laptop. Only skiing stickers, that is. If you want to see these laptops or check out some of the inventory of pictures they have, go to stickertop.art. And if you want to learn more about the open source projects I covered in the programming languages story, see the links in the show notes. And here's the other technology news for the day. The Network Time Foundation, which supports the NTP project, it's currently fundraising with an $11,000 monthly goal, and it's raised $4,675 as of this writing. NTP, Network Time Protocol, is widely used to synchronize computers and networks across the internet, often using GPS clocks as inputs. But GPS satellites themselves aren't usually synchronized by NTP. They carry their own atomic clocks. For high-precision financial compliance, firms typically use something called PTP or GNSS timing in addition to or instead of NTP. But Network Time Protocol is the thing that usually keeps your time right on your computer, on your servers. It's really time to act to save the time protocol. And I want to note how surprising it is that something as fundamental as the NTP protocol has to raise money. In light of the other 2 programming stories that I reported today, we're in the middle of a weird crisis. We have trillion-dollar companies using open source, but yet some of them have to go beg for funding. So if you have an extra $5, go look at the show notes and go to the NTP project and give it. It's time to save time. And our last story is also the feature of this episode. A severe solar storm has caused the northern lights to be visible as far south as Texas, Alabama, Georgia, and northern Florida. I also saw it in Seattle last night. Now, last night's G4 storm is predicted to be followed by another one tonight. And while it's stunning visually, it also may cause voltage control issues in power systems and some disruption to GPS navigation. I'm going to talk more about this in the remainder of this episode. But that's today's technology news for November 12th, 2025. And if you're interested in any of these stories, once again, please see the show notes for links. If you were lucky enough to have clear sky last night and you lived anywhere north of, say, Arkansas, you were likely able to look up into the sky and see some phenomena that's called northern lights. It's an aurora. If you were further south, say Alabama or Arkansas, you saw a bright red glow on the horizon. And if you lived in a city like me, in Seattle, you were able to see a faint glow that was green, at times red. If you're lucky enough to live in the middle of the country with very low light pollution, you saw a fantastic show last night, especially if you lived in a northern latitude. And what's amazing about this is that it's predictable. You can get a warning. There's also a whole community of people that share pictures. I'm in one of those from Facebook, and last night, I could tell you, it was lighting up. Everything was active. And this happens maybe once or twice a year. You usually don't hear about it, but last night was exceptional. Not as exceptional as the storm we had last May, which was a G5, or an extreme event. And that was something that happens maybe once every 20 years. But when you look up at that sky, you're seeing the visible aftermath of explosions happening 93 million miles away that release more energy than billions of nuclear bombs. And I hate to keep on using nuclear bombs as a comparison for energy, but it's something that all of us are familiar with. Right now, I'm also preparing to sing in a concert called Northern Lights next month, and I've been diving deep into both the science and the cultural impact of what we call the Northern Lights. So I want to start with the unimaginable scale of solar power. And let me put the sun's power in perspective for you. The sun is basically a 4.5 billion-year-old nuclear fusion reactor. And it's about 865,000 miles across. That's over 100 times wider than the Earth. Every single second, it fuses 600 million tons of hydrogen into helium. And that releases 3.8 times 10 to the 26 watts. And that number doesn't make sense. And neither will this one. That's 380 yottawatts of energy. And just to wrap your head around that number, that's the equivalent to 90 billion megatons of TNT exploding every second. Or think of it this way. It's like 2 billion of the largest nuclear bombs humanity has ever built. That's the 50 megaton Tsar Bomba, detonating every single second. And we're sitting just 93 million miles away from this colossal fusion engine. So when the sun has a particularly bad day, when its tangled magnetic field lines snap and reconnect in what's called magnetic reconnection, it can blast billions of tons of charged particles into space in what we call a coronal mass ejection, or a CME. A strong CME can carry 10 to the 22nd to 10 to the 25th joules of energy, and that's comparable, once again, to roughly a billion Hiroshima-class bombs. So these aren't gentle solar breezes. These are cosmic hurricanes of electrified gas hurtling through space at speeds of up to 3,000 kilometers per second. So when one of these coronal mass ejections blasts off from the sun, it expands as it travels. And by the time it reaches Earth's vicinity, it can be tens of millions of miles across. The fastest ones can cross that 93 million mile gap in as little as 15 to 18 hours. So how do we know they're coming? We, and in the context of this story, we means humanity. I'm not going to talk about which government owns what satellites, but humanity has specialized satellites that are constantly watching the sun. The SOHO spacecraft uses something called a coronagraph. That's basically a device that blocks out the bright disk of the sun so you can see the corona around it. And from these images, forecasters can literally see a CME as an expanding blob racing towards us. Then we have sentinel satellites like Discover, DSCOVR, positioned at what's called the L1 Lagrange point. That's about 1.5 million kilometers from Earth, roughly 1% of the weight of the sun. When the shock front of a CME hits these satellites, they register a sudden jump in particle density, wind speed, and magnetic field strength. And this gives us typically 15 to 60 minutes of warning before a solar tsunami of energy reaches the Earth. So what happens when this wall of charged particles slams into the Earth? That's where the magic really starts. Earth is surrounded by a magnetosphere. and that's the protective magnetic shield that deflects most of these solar particles. Without it, we wouldn't exist. But near the polar regions, our magnetic field lines dive into the atmosphere, creating highways that funnel those energetic particles down toward the north and south magnetic poles. When these speeding electrons and protons slam into our upper atmosphere, typically at 100 to 300 kilometers above the Earth's surface, they transfer energy to atmospheric gas atoms. This is primarily oxygen and nitrogen, and that excitement of these atoms into higher energy states, that's when they start to emit photons. When they get excited and then they get relaxed back down, they emit photons. The cumulative effect of countless such collisions is what you see. The aurora. The colors you see depend on which atoms are excited and at what altitude. So the most common auroral color is a vivid green, and that's what I saw last night. That's atomic oxygen at altitudes of roughly 120 to 250 kilometers. And so when oxygen is excited at that altitude, it emits photons that are green at 557.7 nanometers. At even higher altitudes, excited oxygen produces deep red auroras. So if you saw pictures from Washington or British Columbia last night, they were likely green with a little bit of red. And if you saw pictures from Chicago or Alabama or Arkansas, you were seeing deep red auroras as people were staring up at the top of this excitement. And that was present last night. So this was a fairly large event. You'll also see purple and blue hues, that's nitrogen, and sometimes you see those on the lower borders of auroral displays. So that's what you see, but what do we measure? When you're looking at the reports of a potential aurora event or an ongoing aurora event, the one number you'll see a lot is called the K index. You'll also see a number called proton flux. And I want to explain what those numbers mean, because if you're into this, and you can tell I'm into this, this is the thing that you watch to figure out if it's time to jump in the car and drive out to the country. So the K index is basically the aurora meter. It's a scale from 0 to 9, and it measures how disturbed the Earth's magnetic field is during geomagnetic activity. The KP index is the globally averaged version. Low values like KP 0 to 1 mean that the magnetic field is quiet. But when you get to KP 5 to 6, you're looking at minor to moderate storms where auroras might be visible in places like southern Canada or Alaska or the northern US. When you hit KP 7 to 9, that's when things get more interesting. Very bright, active auroras that can be seen well beyond the polar regions. During severe events like last night, auroras might be visible as far south as parts of the continental United States or Central Europe. Proton flux is a little bit different. It measures the number of high-energy solar protons zipping through space, and it's usually given in a proton flux units of PFU. These protons are high-speed particles typically emitted during most solar flares or coronal mass ejection-driven shock waves. While electrons create most of the visible aurora, these high-energy protons are what create radiation storms. NOAA's S scale defines the thresholds. S1 is minor, 10 PFU, all the way up to S4 severe, 10,000 PFU. And you can see graphs for proton flux, and it usually correlates with K index, but sometimes they don't. It's a very interesting area to study and to keep track of. But last night, for example, one of the signs that we were about to have an amazing auroral display was the proton flux immediately jumped. And they measure the proton flux for different energies of particles. It's complicated. And I'll get into a little bit of where you can go look for this yourself. And I'd also remind you that tonight there's a forecast for another geomagnetic storm. So on a personal note, I'm probably the most interested in this area of everybody that I know. I mean, I'm constantly looking at space weather. I'm constantly looking at the Space Weather Prediction Center. And those are websites that you should check out if you want to track this activity. Coincidentally, last night I was going to choir rehearsal at around 6 p.m. It wasn't fully dark yet, so you couldn't see it, but it was actively visible over Lake Washington, which is just east of Seattle. And I was going to sing with a group that I sing with called Seattle Pro Musica. We're rehearsing for a concert called Northern Lights, music of the Nordic and Baltic countries. And the centerpiece is a choral work entitled Northern Lights by Latvian composer Eriks Isenvalds. Now it's Latvian, so I probably pronounced that name incorrectly, but it's Eriks Isenvalds. Now, what's fascinating about this piece is how it weaves together both the scientific wonder and the ancient folklore of the aurora. Eisenwald was so captivated by witnessing the northern lights in Norway that he traveled through Lapland, Iceland, and Greenland just to observe them. His composition combines text from a Latvian folk song with prose from a 19th century Arctic explorer, Charles Francis Hall, and Fridtjof Nansen. The folk song reflects an old Latvian belief that the aurora are the restless souls of fallen warriors battling in the sky, a haunting interpretation that shows how different cultures have tried to make sense of the phenomena. But Eisenwald sets this against the factual descriptions from explorers who witnessed auroras on their expeditions. Musically, the piece calls for the choir to play tuned water glasses and chimes, and this creates an eerie crystal tone that evokes the shimmering atmosphere of the aurora itself. It's a 6-minute work that truly tries to put northern lights into sound. It ends with delicate chiming as if the lights are fading into the night sky. And it was pretty intense. I might have been one of the only people in the group to know that this was happening because not a lot of people are tracking spaceweather.com on a daily basis like I am. Actually, earlier that day, I sent a note to people I work with just to let them know that there were warnings in place, because what I'm going to talk about in the next section is there are actually some real risks from geomagnetic disturbances. And I don't think that as a world, we're really familiar with them because it's been quite a while since we've faced real impact from a geomagnetic storm. But back to the Seattle Pro Musica side of it, we're having a concert. The tickets for our winter concert usually sell out. It's December 13th, and it's at Bastille, which is in Kirkland, Washington, for those of you who are local. Reach out to me if you want tickets. But back to choir for a second. So I'm in rehearsal. We had a little break. I ran outside to see if I could capture this, and you could barely see it. It was green, slight bluish tint. It was north. I mean, if you looked north towards Mount Baker, it was in that direction. And I think one of the things that's probably the most frustrating to people who track auroras and who like to see them is if you hold up your phone and take a picture of it, it is fantastically magnificent. But sometimes you can't see that level of detail with the naked eye. And knowing me, I'll probably do a whole hour-long episode about why that is. But the thing that you have to do if you really want to see it is drive out to the middle of nowhere. And for me, that's, driving up to a place like Carrington, Washington, and then taking an off-road trail to be close to Glacier Peak. And that's the darkest place I've found that's in driving range. But I snuck out of rehearsal, I took a picture of the sky, and then we rehearsed Northern Lights. So it was a very interesting night. But let's talk about risk, because that's what I like to talk about the most. And I think we need to take this seriously, because we really haven't been alive at a time when we have both a massive number of data centers and a significant geomagnetic storm. Last year, we came closer to it than we ever have. That was a 20-year event. But there are 100-year events that I don't think we're ready for. So when the forecasters issue an aurora alert, it's not just a heads up for people like me to go drive out to the country and see lights in the sky. It's essentially a storm warning from the sun. And the reason we spend so much money on the science and on the tracking is because it actually does cause real disruptions. During an extreme G5 or extreme geomagnetic storm, that's the highest severity on NOAA's scale, widespread voltage control problems can happen. Some grid systems may experience complete collapse or blackouts. Transformers can be permanently damaged. And this isn't theoretical. We've actually seen it happen in the past. In March 1989, again, that's before we had as many data centers as we have today, a geomagnetic storm plunged 6 million people in Quebec into darkness for 9 hours during a frigid winter. Traffic systems failed, airports shut down, district heating stopped working entirely. The sudden geomagnetic surge induced currents that overwhelmed the power grid and damaged equipment. But that's nothing compared to what could happen. The Carrington Event of 1859 was the most intense solar storm on record. It electrified telegraph lines, shocking operators and setting telegraph paper on fire. If a Carrington-class storm hit today, it could cripple communication networks, disrupt the power grid, and cost the global economy trillions of dollars. Yes, trillions of dollars. A 2013 study estimated that such an event, a Carrington-class event, would cause $2.6 trillion in damage worldwide. And we came terrifyingly close to finding out firsthand. In July of 2012, a colossal solar eruption narrowly missed the Earth. Researchers believe that it was at least as strong as the 1859 event. As space physicist Daniel Baker said, if it had hit, we would still be cleaning up the pieces. So why are we so vulnerable? Because the same solar energy that creates beautiful auroras can overload the technologies that we depend on. Geomagnetic storms induce electric currents in long conductors, power lines, pipelines, undersea cables, and that can cause cascading failures or transients across interconnected systems. A severe space weather event could disrupt electrical grids, causing blackouts that halt water treatment, heating and cooling systems, fuel pipelines. GPS systems could fail, affecting everything from navigation to precision agriculture to financial timing systems. Vehicles and small electronics are not directly at risk from geomagnetically induced currents, but outages and GPS disruptions can seriously impede operations. And as connected as we are, they can bring society to a complete halt. The May 2024 geomagnetic storm was the strongest in over 20 years, but it caused only minor disruptions. It did serve as a wake-up call. A Bloomberg intelligence report noted that a truly major space storm could cost more than Hurricane Katrina in insured losses. Another analysis found an extreme solar event could inflict 0.2 to 1.2 trillion in direct economic losses to the U.S. alone. Perhaps more concerning, damage to high-voltage transformers can take months or years to repair. And these giants of the grid are custom built by only a few global manufacturers. Back orders could stretch for 2 years or more in a crisis. So the good news is that we're not completely helpless. Unlike earthquakes or hurricanes, we can see solar storms coming. Sun monitoring satellites give us hours or days of lead time. NOAA's Space Weather Prediction Center coordinates with industries to prepare. Satellite controllers can put spacecraft into safe mode. And power companies can proactively adjust grid loads in advance. One study estimated that timely space weather forecasts help the U.S. power industry avoid up to $27 billion in losses from a single severe storm by enabling those proactive steps. So it's well worth the investment. But the awareness is key. The next time you see an aurora warning, remember that you're not just looking at a light show. If you're responsible for data centers or power grids, you're witnessing evidence of a solar storm that could potentially disrupt the technological infrastructure our civilization depends on. And for an example, last May, there was a degradation in performance for the Starlink service. There was a power grid in New Zealand that suffered problems. If that storm had been 2 or 3 times more powerful than it was, it would have disrupted the things that you use every day. So instead of betting on continuing to be lucky, I think we need to prepare for this as a potential risk. Because while we were lucky in 2012 to avoid that 1859 Carrington event, that might not always be the case. The good news, though, is that even if the worst happens, it'll be amazing to watch. So the next time you're watching those lights in the sky, remember you're looking at a visible manifestation of forces beyond our comprehension, explosions that dwarf our most powerful weapons by orders of magnitude. And these are particles that have traveled 100 million miles through space to interact with particles high up in the atmosphere. It's amazing. And if you've never seen it, I actually would recommend traveling to see it. It's worth it. But also remember that that same fury that creates beauty could also, on a bad day, send us back to a pre-electric age. Because I also have to add in, just for fun, that 1859 event might not even be the largest possible event. So, anyway, I know people who listen to my podcast are like, you worry too much about the weirdest things. But our civilization is remarkably fragile. I think it's time for us to start thinking about this both as beauty, but also as risk. So if you want to also appreciate the beauty of music that's inspired by the Northern Lights, I would encourage you to purchase a ticket for Seattle Pro Musica's December 13th concert at Bastyr University entitled Northern Lights. And with that, thank you for listening. And I hope we have a good show tonight. But I hope it's not a really good show, because if that happens, then we might be in serious trouble.